Hey guys, Mrs. Traver here. We're going to do our notes on section 4.4, graphs of logarithmic functions. In this section, you will graph logarithmic functions, identify the domain of them, as well as the range, and then we'll look a little bit at inverse functions and how these came to be. Let's see if I can get this off the screen. There we go. So the first thing I want to do is look at a function that we are familiar with. This graph didn't show up very well, so I'm going to bold it in for us. This graph is one that we've seen before. It is that of y equals 2 to the x. And when we are dealing with these functions, the new one that we're going to come across today is the logarithmic function. And kind of how it came to be is that we had this function y equals 2 to the x, and every function must have an inverse. And inverse functions are made by reflecting across the line y equals x, which is this dashed line. So this function is y equals log base b of x. And that's the one that is graphed here. Hopefully that focusing doesn't happen this whole video. Okay, so the main thing that I want to mention here with this function is that whenever we do an inverse, we switch x and y, and that happens with the graph as well. So notice there's a point 0, 1 on this graph, and on this one it's 1, 0. So we'll notice that switching around, especially in this table. So here's the top one is our purple one over here, and the bottom one is the pink one, the log function. And notice all these points are just flip-flopped. So where there's an x in the next function, it's the y, and where there's a y in the next function, it's the x. These are the ones that we really spent some time with when we graphed exponential functions, 0, 1, and 1b. And now they just got moved around to be 1, 0, and b1. So those are the parent function points we're really going to focus on, is that of 1, 0, and b1. And then the b comes from the base of the log. So before, our b in this case was 2, because it was the thing that was to the x. In this case, it's down there as the base of this log function that we're dealing with. So this is how the transformation function will look. Y equals a times log base b of the quantity x minus h plus k. And this a and h and k will work the same way they always have, whereas x gets affected by the h value, it's left and right, and it works the opposite of what you'd think. So if it's plus, it's going to go left. If it's minus, it'll go right. The y is affected by a, where either a can be a reflection or a compression or a stretch. And then also it can be affected by k, which is an up-down. So these are the same things that we've been dealing with before. The other thing that I want to bring your attention to while we have this graph up here is remember when we had the function y equals 2 to the x, there was an asymptote line at this x-axis that said you can't cross that. There's no function below it. You'll get really, really close to it on the left, but you'll never touch or cross it. Well, seeing how we are dealing with a inverse function and all the x's and y's are traded, our inverse is now at the other axis. So our inverse in this case is x equals 0 for this function. And it's actually found by using x equals h. So that is our asymptote. That we'll use in each one. So let's jump into it and do an example. I'm going to zoom out a little bit. So it says graph the function, give the domain, range, and asymptote. So let's try it. Number 1. Y equals log base 2 of x. And we'll deal with our parent first. Our parent function has the points 1, 0, and b1. And in this case, b is 2. Let me see if I can get it to stop doing that. Maybe that'll be better. We'll see. Okay, so that's our parent function, and we have no transformations here. There's no a out front. There's nothing with the x in parentheses. There's no k outside. So nothing's moving. It's going to stay 1, 2, 0, 1. We can plot those points. So I've got a point at 1, 0, and at 2, 1. And then my asymptote line, in this case, there is no h, so it's going to be at 0. So it's right at the axis where we can't cross. And now we can connect our points. So we're going to get closer and closer to it on one side and further and further away on the other. So domain is wherever the x's can live, and we've set our asymptote to say that they can not cross and come over here. So it's everything to the right of 0. So x greater than 0. Our range, however, it goes as far down as it wants, as well as far up as it goes. So it hits everything, all reals. And then our asymptote line, as we mentioned earlier, is that line x equals 0. All right, let's try another one. We'll do several of these. This one is a base 5, so I've got the points 1, 0, and base, which is 5, 1. And let's see, this one has a plus 2 with the x's. That's an h value. So in this case, h is opposite of what you see. So h is negative 2. That means I'm going to go left 2. So let's show that by moving my x's left. So 1 left 2 is negative 1. 5 left 2 is 3. 0 and 1, that y values, because there's no k, there's no a, they're not getting affected, so they're going to stay 0 and 1. So I've got a point at negative 1, 0, and at 3, 1. And then because my h is negative 2, that's where my asymptote will lie. If you have a pencil and don't have two colors, I suggest trying the asymptote in a dashed line. So let's do asymptote since we're right there with it. It's at negative 2, so x equals negative 2. And then domain goes right along with it. I guess I should graph my function. It'll go something like that. Our domain is everything to the right of negative 2, so x greater than negative 2. And then range, all reals, everything top to bottom. Let's try another one. Okay, let's see, number 3. We've got log base 4 of x minus 3, so we've got the point. Let's see, we've got the point, 1, 0 and b1. 1, 0, b1, and in this case our b is 4. And we've got a minus 3 out here, so that's going to be a down 3. And that'll affect the y's. The x's won't get affected at all. So since the x's aren't affected at all, they're going to stay 1 and 4. The y's, however, like we said, will go down 3. So we'll go 0, minus 3, 1, minus 3. Then we've got our points to plot. 1, negative 3, 4, negative 2. And then our asymptote, there is no h value. The h value is the one in parentheses with the x. There's no h value here, so it's going to be at the axis. It's hard to draw on a line that's already there. So we've got closer and closer on one side and off towards infinity on the other. So our asymptote we said was at the axis, so that's at x equals 0. Our domain is everything to the right of 0, x greater than 0, and then range is all reals. Let's look at the next one. We're just going to keep moving along here. This one has two different transformations happening. So again, 1, 0, b1, and in this case, b is 3. Let's look at the transformations we have. We have an h of negative 2, and we have a k of negative 1. That h equals negative 2 will tell us we're moving left 2. And that k equals negative 1 will tell us we're moving down 1. So both of those things will happen corresponding. So let's see, our left 2, 1 left 2 is negative 1. 3 left 2 is 1. 0 down 1 is negative 1. 1 down 1 is 0. We have our points to plot, negative 1, negative 1. 1, 0. And since h is negative 2, then that means our axis, our asymptote, that's what I was saying, is right there at negative 2. we've got closer and closer on one side, off to the infinity on the other side. So our asymptote was there at x equals -2. Our domain, everything greater than that asymptote -2. And our range, all reals. We'll do two more. The next one has a fraction. So same thing, even though it's a fraction. 1, 0, and b, 1. In this case, b is 1/2. We have a k value of 2. That's going to move us up 2. And our x's are not affected, so we'll leave it as 1 and 1/2. Our y's will go up 2, so from 0 up 2 to 2, from 1 up 2 to 3. We've got our points, 1, 2, 1/2, 3. And then because, again, there was no h value, there was nothing in the parentheses with the x, our asymptote is at the axis here. We'll get closer and closer on one side, and further away on the other. Notice this graph, this curve looks slightly different than the rest. It looks like it's going down, and that's because it's a inverse of a decay function. That's where the b came into play. So let's see. Our asymptote on this one was at the axis, x equals 0. Our domain was everything to the right of 0, x greater than 0. And then our range was all reals. All right, last one of these. Log base 5 of the quantity x minus 1. So let's see, I've got my points on my parent 1, 0, and b, which is 5, 1. I've got a right 1 because h equals +1, opposite of what you see. So these will move right 1 will move to 2, 5 will move to 6, y's will stay the same. Point at 2, 0, point at 6, 1, and an asymptote at 1. So here is our curve. We've got an asymptote at 1, a domain x greater than 1, and a range of all reals. All right, we've done lots of examples, 6 of them of the graphing. Let's move forward. All right, so this next piece is talking about inverse functions. It says, by the definition of a logarithm, it follows that the logarithmic function g of x equals log base b of x is the inverse of the exponential function f of x equals b to the x. So basically it's just saying, hey, you know how these are inverses of each other? Remember how inverses, the transformations of them, are equal to x. So if this is g and this is f, if we do a composition of them, like g of f of x, it'll equal x. They took g and they plugged in f of x into the x, or right here, and it looks like this crazy business. They said that will equal x, and then similarly the same over here with the other way. So what this will do is help us to find the inverse of a function algebraically. As you remember, finding the inverse has 2 steps, which is to switch x and y. And then secondly, solve for y. Pretty straightforward. So let's do that. Let's switch x and y. Now we've got x equals log base 3 of x. And we've got our log by itself. We want to, oh wow, I did not really switch those. How about this is a y, so sorry. We want to get rid of that log base 3. So like normally when we're solving equations, like for example, say I had 2x equals, y plus 3, and I want to get y by itself, I would have subtracted 3. Like subtracting is the opposite of adding. Those are inverses of each other so that we can cancel it out and get y by itself. So similarly on here, I want to get y by itself, but it's got this log base 3 on it. So what we'll do is we'll take both sides with that base. We'll say 3 to the on both sides. So let me show it to me. We'll say 3 to the x, because that was on one side. The other side to the log base 3 of y. Which looks a little strange, but the deal is we're trying to cancel things out. So that's why we do weird things like say minus 3 plus 3. So we're doing 3 to the log base 3. Those will cancel. So I'll have 3 to the x equals y. All right, let's jump to number 8. This one, we want to get the x's and y's switched up first. So let's say x equals 9 to the y. And I want to get rid of that 9, so I'm going to have to do log base 9 of both sides. So on the left, I've got log base 9 of x. On the right, I've got log base 9 of 9 to the y. And we do this so that this log base 9 of 9 to the something will cancel. I've got just y on the left, on the right. On the other side, I've got log base 9 of x. Let's do another one. This one, it looks a little bit different, and I'm going to kind of go off to the side for a moment and tell you something special that we'll learn more about next section. Log base e, we write that, so remember e is approximately 2.7. It's that special number, Euler's constant. So log base e, we write that as ln, I'll say log base e of x, I should say. We write that as ln x, and it's read as natural log. Don't say ln x, even though that's the way it's written as natural log. The reason why we write it with ln instead of nl is because l looks like 1. And sometimes if there's a number in there, like if you were going to try to say the natural log of 7 and you wrote it nl7, it looks like n17, which is weird. So natural log, even though the letters are switched, we don't say ln, we say natural log. I will correct you on that. So this natural log just means we have base e. So y equals natural log of the quantity x minus 2. I want to switch x and y to start. So x equals natural log of the quantity y minus 2. And then to get rid of that logarithm on both sides, that natural logarithm on both sides, we need to take everything to the base that the natural log has, which is e. So both of these sides will say e to the, and I can kind of be clever in just putting an e there underneath of it and kind of making those become the exponents. So if you do that, you kind of save yourself a step in writing it. And then this e to the natural log of something something will cancel. So I've got e to the x, let me rewrite, equals y minus 2. I don't quite have y by itself yet. Let's add 2 to the other side. So we've got y equals e to the x plus 2. All right, last one. Y equals 5 to the x plus 6. So let's see, we want to get the thing that is to the x by itself first. Actually, no, first we need to switch x and y. Let's do that. Getting ahead of myself. Now we want to get the thing that is to the y by itself. So let's move the 6 over. And now we've got the 5 to the y by itself. I can take both sides to their log base 5. Log base 5. Log base 5. So on my left, I've got log base 5 of x minus 6. And on my right, I've got log base 5 of 5 to the y. Be careful and use parentheses here. I've done it on both of these examples. It didn't matter as much here because I only had one thing that I took to the log. This time it does matter, definitely, because of the fact that you had that minus 6 there. So these will cancel. And on my left, I've got log base 5 of the quantity x minus 6 equals y. The rest of this is like, if you'd like to try it on your own, you totally can. When I post my key, I will put the answers to these up as well so you can see them and check how you're at. Other than that, I will see you guys next time.